That arrow is a vector with components x and y, and the question is, if it was rotated, then what are the new components? And here's the answer. X and y become cos theta x minus sin theta y and sin theta x plus cos theta y. And I could also write it like this by taking those terms out. That table is called a matrix and it encodes the transform. And to go back, just distribute the x's and the y's. This matrix encodes doing nothing. It's called the identity. It's also a 0-degree rotation. J here is a 90-degree rotation matrix. It takes 2, 1 to minus 1, 2. And one property is that if we apply J again, then the result is to just flip the vector over or make it its negative. So J squared is minus the identity, quite similar to how I square is minus 1. The rotation matrix can be derived with trigonometry, but that's not very fun. And it was Sophus Lie who solved this problem for us with a very obvious idea. To rotate by a finite angle, you rotate by a very small angle many times. It's like animation. By the heads to tails method, the rotated vector is just the sum of the other two vectors. And as it is a very small angle, the small vector is just g rotated by 90 degrees and then scaled down. So it's g plus jg divided by the length of g to make it unit length, and then scaled by the length of the small vector, which is roughly the length of the arc connecting the 2 points, which is radius times the angle measured in radians, so length of g times theta by n. And on cancelling the lengths and factoring the g, we get the infinitesimal rotation matrix. And r of theta is just that raised to the nth power, and then we take the limit as n goes to infinity, which is e raised to theta j. Like e is that number and you can see the similarities. But wait, to actually calculate this, you would expand r of theta, and as n goes to infinity, you'd be left with the power series expansion of e raised to theta j. You have to understand though how this is actually obvious. A rotation matrix by alpha times a rotation matrix by beta is a rotation of alpha plus beta degrees, which is just like the exponent property. And now we know that rotations are exponents. J square is minus I, right? So similar to Euler's famous formula, we get the rotation matrix. These infinitesimals are quite useful in the study of symmetry, higher dimensions, other transforms, differential geometry. What you need is your J, the generator of your transform.